Welcome to lecture 13. We'll summarize the equivalent characterization of a valuation ring that we've collected so far. So we'll call this theorem 35. So let B be a domain with fraction field K. The following statements are equivalent. So the first statement is that for every alpha that's not 0 in K, we have alphas in B or its inverse is in B. This is what we call the V ring. And the second property was that for any two ideals, say I1 and I2 of B, we have I1 sits inside B or I2 sits inside I1. Sorry, I1 sits inside I2 or I2 sits inside I1. This is what we call a V star ring. The third property was that ring B is the valuation ring of a valuation on K cross for some totally ordered abelian group. And B, the last property is that B is a local ring that is maximal under domination. Okay, so we've seen that property of being a V ring and a V star ring, these are equivalent. So this was in lecture 8, proposition 17. We've seen that being a valuation ring means that you are a V ring. This was lecture 9, proposition 25. We've also seen that if you are a V ring, then you're a valuation ring. This was lecture 10. This was a combination of propositions 30 and 31. And we've seen that if you are a V ring, then you're maximal under domination. This was lecture 11, proposition 32. Then finally, last class, we saw that if you're maximal under domination, if you have the property of being maximal under domination, then in fact you're a V ring. So this was proposition 34. So all these statements are in fact equivalent, and any ring satisfying the above equivalent conditions will be called a valuation ring. So I'm no longer going to use the term V ring. So I'll just use the terminology valuation ring. And so I just want to give an exercise to you. And just as earlier, this is an exercise using Zorn's lemma. So suppose inside this field K, you have a local ring. Then the first question that I want to ask myself is there a valuation ring that contains A naught? And so the exercise is that that's true, and it's an exercise using Zorn's lemma, that abstractly you can show that there exists a valuation ring V that not only contains A naught, but it actually dominates this local ring A naught. Okay, and the hint, or the proof sketch, is just to use Zorn's lemma. So what you first do is you just consider the collection sigma, which consists of all local rings. So let's call it CIMI, with CI being the local ring inside K with maximal ideal MI, says that it dominates A naught, this local ring A naught. And note that this collection sigma is non-empty, since A naught itself with its maximal ideal M naught belongs to sigma. So here M naught is the maximal ideal of A naught. So A naught dominates A naught almost by definition. So this A naught comma M naught belongs to the sigma. And what you do is you impose this partial ordering by domination. That is, given C1 M1 and C2 M2 in sigma, so we say that C1 M1 is less than or equal to C2 M2 if C2 dominates C1. So again, that means that there exists an injective ring homomorphism P from C1 to C2, says that it maps the maximal ideal into the maximal ideal of C2. Okay, and so just verify that this in fact is a partial order. And the idea is to apply Zorn's lemma so given any, say, totally ordered collection, let's call it sigma 1, where you have pairs CIMI inside the sigma for some indexing set I, then one can get a maximal element for this totally ordered collection. And so there's not much you could do. So you have to choose some C tilde M tilde as a choice of this maximal element in sigma. And so it should dominate all the CIs. So you just let the ring be the union of all the CIs, and the maximal ideal be the union of all the MIs. And so because you have a totally ordered collection, you can show that C tilde is in fact a ring with maximal ideal M tilde. Okay, and now using Zorn's lemma, show that this collection sigma has a maximal element and call it, say, C prime M prime, and then prove that C prime is a valuation ring by proving that it's maximal under domination. So it satisfies property 4 of theorem 35. This was the property that it's maximal under domination inside K. Okay. So I want to use this exercise to study some property about integrally closed domains. So suppose I have a domain inside a field K. Now you choose any maximal ideal, say M of A, and then what we have is that A sits inside the localization and everything sits inside the fraction field K. So let's call maybe K as the fraction field of A. And now what does this exercise guarantee us? So it guarantees at least one valuation ring V inside K that dominates this localization and hence contains A. So maybe there's one valuation ring containing A, maybe there are several. So now A sits inside the intersection of all the valuation rings inside K containing A. Okay, so just for short, so we denote, so I don't want to keep writing valuation rings inside K containing A, so we'll just denote this as the intersection, and I'll just put a star in below. Okay. So in general, if you take any domain, you look at all the valuation rings containing A inside K, you take the intersection of all of those, you have this inclusion, and you can ask, when does this inclusion become an equality? So one partial answer to that is, suppose A is an integrally closed domain, then in fact we do have equality. So A in fact equals the intersection of all the valuation rings inside the fraction field K that contain A. So again, what's the proof? So we have that A sits inside this intersection and everything sits inside K, which is by definition the fraction field of A. And now a small claim. So given an element alpha that's in K but that's not in A, what I'm instead going to show is that there exists a valuation ring it's called V alpha inside K that contains A, but it doesn't contain alpha. Okay, so here's a claim. Now before proving the claim, let's see why the claim implies the proposition. Now suppose the claim is true, and if you have an element, so you take an element alpha that's in K but not in A, then you have this element, this valuation ring V alpha, and alpha does not belong to V alpha, and hence alpha does not belong to this intersection of valuation rings inside K containing A, and this just means that alpha belongs to K minus this intersection. So in other words, what the claim allows us to see is that K minus A sits inside K minus this intersection. And now if you just take set theoretic complements, so the direction of inclusion reverses, so you get that A contains this intersection. So we have that A contains this intersection, but A also sits inside this intersection. So in particular, what the claim allows us to show is that A equals this intersection. So it's enough to prove the claim, and that's what we'll do now. So you take an element alpha that's in K but not in A. Now what's the goal? The goal is to prove the claim. So I want to find a valuation ring V alpha inside K that contains A but that does not contain alpha. So I'll first construct this ring A, which is A adjoint 1 over alpha, and again everything sits inside the fraction field K. And now one observation is that alpha cannot belong to A1, and again why? Because if it did, well, what's A1? It's the smallest ring containing A and 1 over alpha. So you can write alpha as a polynomial expression over 1 over alpha with coefficients in A. So you can write alpha as A naught plus A1 1 over alpha plus A2 1 over alpha square plus so on and so forth AD 1 over alpha to the D, where these coefficients A naught, A1 up to AD belong to the ring A. And then if you just multiply throughout by alpha to the D, what do we get? We get alpha to the D plus 1 minus A naught alpha to the D, I'm just rearranging things, minus A1 alpha to the D minus 1, so on and so forth, minus AD equals 0. And so now I get that alpha satisfies this integral equation, so alpha is integral over A because it satisfies this monic equation, but that must mean that alpha belongs to A since A is integrally closed in its fraction field. But this is not possible by assumption. I chose this element alpha to be in K but not in A. Okay. So our assumption that alpha belongs to A1 is false, so the observation is correct. So in particular, so thus the observation is correct. That alpha does not belong to A1. Okay. In particular, so since alpha does not belong to A1, well, what do I know about 1 over alpha? Well, 1 over alpha does belong to A1 because it's A adjoint 1 over alpha. But is it a unit in A1? 1 over alpha now cannot be a unit in A1. Why is that? Because its inverse alpha does not belong to A1. An element is a unit in the ring if and only if its inverse also belongs to the ring. But I have that 1 over alpha belongs to A1 and its inverse alpha does not belong to A1. So that allows me to conclude that 1 over alpha cannot be a unit in A1. And so you just pick a maximal ideal, say M alpha. Since 1 over alpha is not a unit, I can find a maximal ideal M alpha that contains 1 over alpha. And now consider the local ring given by the localization with respect to this M alpha. So let's call that ring C. So I'm just localizing A1 with respect to M alpha. So this is a local ring. With maximal ideal, I'll call that MC. And that's given by the localization of M alpha. Where this SM alpha is just A1 minus M alpha. So now just collecting all our inclusions, I have that A sits inside A adjoint 1 over alpha. That sits inside C, which was the localization of A1 over alpha. So A1 over alpha is what I call A1, and A1 over alpha localized at M alpha is just A1 localized at M alpha, and everything sits inside K. And now what I have is that 1 over alpha belongs to M alpha, and that sits inside the localization of M alpha, that's MC. And now you apply exercise 36 again to the local domain C, and what that allows you to deduce is that there exists a valuation ring V alpha inside K. Let's call the maximal ideal MV alpha. And what this exercise allows you to conclude is that it dominates C. So again, what do we have? I have A sitting inside A1, which was A adjoint 1 over alpha. That sits inside C, which sits inside this V alpha. So let's call that inclusion phi. And what we have is that V alpha dominates C. So if I look at this ring inclusion given by phi, the maximal ideal of C sits inside the maximal ideal of the valuation ring. And what I have is that 1 over alpha belongs to M alpha, and in particular belongs to MC. And so what that allows you to deduce is that 1 over alpha, it belongs to MC, so it must belong to the maximal ideal of the valuation ring. And so thus 1 over alpha belongs to the maximal ideal MV alpha of the valuation ring V alpha, and thus 1 over alpha is not a unit because it belongs to a maximal ideal. So it's not a unit in V alpha, and so its inverse cannot belong to V alpha. Thus its inverse alpha, so its inverse in K, cannot belong to V alpha. So now we produced a valuation ring V alpha with the property that it contains A and it does not contain alpha. Thus, we produced a valuation ring V alpha inside K containing A but not containing alpha. And so this proves the claim, and we've already seen that if you prove the claim, we've proved the proposition. This proves the proposition that if A is an integrally closed domain, with fraction field K, then it is the intersection of all the valuation rings that contain A. So it's the intersection of all the valuation rings inside K containing A. Thank you.